So, today we will actually consider a converter which is actually different from the other circuits we have seen so far. Say the converter is just consisting of 6 valves, the ones which you have studied, 6 pulse converters. But what is different in the circuits is the model of the AC side and the DC side. Okay. Now, we will consider actually a different converter where the circuit of the converter itself is different. So, in addition to the 6 valves, we will have what is known as capacitors on the AC side. So, what we get is a capacitor commutated converter. So, a capacitor commutated converter is same as the line commutated converter with some addition. So, I have 3 legs corresponding to the 3 phases of the AC side, and in each leg there are 2 thyristor valves. So, there is an addition of a capacitor in each phase on the AC side. So, there is a series capacitor on the AC side. So, I will call these valves as 1, 3, 5, 4, 6, 2. So, there are 2 terminals on the DC side, the DC side terminals, and 3 terminals on the AC side. So, this is the circuit of a capacitor commutated converter. So, in addition to the 6 thyristor valves, you have 3 capacitors. So, again, if I want to explain what is the necessity of having a capacitor, what we will do is we will try to take a circuit that is a model of the AC side and the DC side. The simplest model on the AC side is just a 3-phase voltage source. The simplest model on the DC side is a constant current source. So, first we will consider the simplest model. Of course, we will not be going into any detailed model, but one can easily extend this to any other model of the AC side or DC side. So, I have a constant current ID on the DC side, the voltage, the instantaneous voltage on the DC side is Vd. And the AC side is represented by a 3-phase balanced sinusoidal voltage source. So, the capacitance of all these capacitors is C. So, they are identical capacitors. So, EA, EB and EC are 3 balanced voltages. So, we will use the same expression for EA, EB, EC that we have been using, root 2 by 3 V sin omega OT plus 150 degrees. EB is root 2 by 3 V sin omega OT plus 30 degrees, and EC is root 2 by 3 V sin omega OT minus 90 degrees. So, we already have a notation for the currents that are flowing on the AC side, IA, IB, IC. We use some notations for the voltages across these capacitors, VA, VB, VC. So, I call this as VA, the instantaneous voltage across this capacitor in phase A. Similarly, this is VB and this is VC. So, we will analyze this circuit. So, in the process, of course, we will see what is the purpose of having a capacitor there on the AC side. So, we know that when there is no inductance on the AC side, the current can be changing suddenly. So, at any instant only two valves are conducting, either 1 and 2, 2 and 3, 3 and 4, 4 and 5, 5 and 6 or 6 and 1. Okay. So, there are 6 intervals, and in each interval any two, one valve from the upper commutation group and one from the lower commutation group is conducting. Okay. So, for the sake of explanation, we will try to look at one of the capacitor voltages. So, we have been using this notation alpha. So, what is alpha? So, it is the instant at which valve 3 is turned on. So, instant, see, though I say instant, I mean its angle, okay, because most of the times our independent variable is angle, instant at which valve 3 is turned on. So, let us try to plot the voltage across the capacitor in one of the phases, say B phase. So, suppose I want the plot of VB. Okay. So, if I want plot of VB, what should I do? How can I get plot of VB? VB is the voltage across the capacitor in B phase. So, how to get the capacitor voltage waveform? Why should I write KVL equation? I mean, why? What is the voltage? Say, if I want the voltage across the capacitor, can I not find the voltage by knowing the current? Capacitance is known. So, can I not get the expression for VB if IB is known? Now, what is IB? So, have we already seen the waveform of IB? See, suppose the capacitors are not there. We know IB. Now, will anything change as far as the currents IA, IB are concerned? If will these currents change due to the presence of capacitor? Is a question. See, we said it is still 2 valve conduction mode. So, it is still 2 valve conduction mode. So, as long as it is 2 valve conduction mode, let us assume 2 valve conduction mode, then say it is allowed actually, 2 valve conduction mode is allowed here. So, that is the only thing, 2 and 3 will not happen because we will see that there is no inductance on the AC side. So, if it is 2 valve conduction mode, then we know the waveforms of IA, IB, IC. So, what are the possible values of IA, IB or IC? It is ID or minus ID or 0. Okay. So, suppose I take the waveform of IB. So, let me plot IB first. So, from IB I can get the other waveforms. Okay, what I will do is, so this is omega OT. Suppose I plot IB. I start plotting from alpha. Okay. So, at alpha, what is IB? It actually goes from 0 to ID. It goes from 0 to ID. So, it is 0 at alpha till alpha and it goes to ID. And it remains at ID for how many degrees? 120 degrees. Then it goes to 0. For how long it remains at 0? 60 degrees. Then after 60 degrees it again goes to minus ID and it remains at minus ID for 120 degrees. Then again it goes to 0. it remains at 0 for 60 degrees, and then it becomes again ID and the cycle repeats. Okay. So, I have IB equal to ID R minus ID R 0, and this is alpha, and this duration is so this duration is 120 degrees. In radian it is 2 pi by 3. So, I will show this in radian. So, let me show these distances in radian. So, this is pi by 3, this is 2 pi by 3, and this is pi by 3. So, if this is IB, what is VB? So, go back to the circuit. See, if you look at the circuit, what is VB? VB can be related to IB. Huh? How VB and IB are related? 1 by C? Integral IB. So, I can write IB as C dVB by dt. So, I have to take a waveform for VB such that its derivative is similar to IB, of course, except for that constant C. C is a constant. So, except for C, the derivative of VB should be similar to IB. So, that means if I want VB, okay, let me use a different color. Suppose I want VB. Okay. So, how will VB vary from alpha to alpha plus 120 degrees? It increases linearly. Okay, it is a linear function, it is ramp. Okay. Then from alpha plus 120 to alpha plus 180, decrease, constant, it is constant. Then when IB is minus ID, negative, then it decreases linearly. Then again for another 60 degrees it remains constant. Now, the question is, if I plot VB, it is like this. Okay, let me. So, it increases linearly, then it remains constant for 60 degrees, then for the next 120 degrees it decreases linearly, then again it remains constant. Then the cycle repeats, it again starts increasing. So, before alpha it would have remained constant. Okay. So, let me just now, what should be the average value of VB? What do you expect the average value of VB to be? Okay. So, I forgot to use the, what should be the average value? Huh? Huh? Looks like looks like it will be 0. Why? Why it should be 0? And the two are not certain. Yeah, I am asking you to just guess. Okay, why it should be 0?
Because IB is like symmetry across x-axis. So you will also have.
Sorry? No, I say when I know current through the capacitor, I need not worry about anything else in the circuit. Say IB is known to me. IB is known to me. So, when I know the IB is the current through a capacitor, so from IB I am trying to plot VB. but the only question that can't be answered using this IB is what is average value. So, average value, I mean, it should depend on the initial value. Now, the question is, even if initial value is not known, can we plot VB is the question. Huh? Sorry? What axis? I have not drawn because I don't know average. If I knew the average, I would have drawn. I have deliberately not drawn the axis, omega OT axis, that because I don't know the average. So, what is average? Huh? T tends to? See, okay, when in steady state, what should be the average?
Actually, average will be 0.
Why?
Because Q is equal to CV and the charge is current into time. So we see that the same amount of charge is getting into the capacitor and the same amount is coming out. So
Yeah.
on
See, the
average, there is no charge.
answer is it depends on the initial charge of the capacitor. But what happens in practice is something different. See, we have taken an ideal case. See, look at the circuit that we have considered on the AC side. Just a voltage source. That is an ideal case. In practice, it is an voltage source in series with inductor, in series with resistor. So, whenever there is a resistor, you will see that there will be always decaying. So, any DC value will decay to 0. See, the resistor will ensure that on the, if you look at the AC side, any DC value will decay to 0 because of the resistor. Now, this resistor is something which is always present. Of course, we have not modeled it. So, we have ignored that. Okay. So, assuming that there is a very small negligible resistance, we can always say that the steady state waveform. So, I am always trying to plot only steady state waveforms, no transient analysis done here. So, steady state waveform will have an average value of 0. Okay. So, that can't be inferred from the circuit that I have drawn. So, that can be inferred only by the fact that there is always a resistance, only thing is we have ignored that resistance, that is all. So, the plot is something like this, where the average value happens to be 0.
So that argument is not valid.
Which one?
The same charge is going in.
See, when you just take a circuit without resistor, it is only dependent, okay, with if the initial charge is say 0, okay, so it can have a non-zero average value. It can have a non-zero, okay, let me just slightly deviate, okay, let me slightly deviate. I have this circuit, okay, I have an inductor. Suppose this is sin omega OT. Suppose this is 1 Henry. The switch is closed at t equal to 0. Then the current flows after closing the switch. So, if I plot the sin omega OT, I know sin omega OT, it is like this. This is sin omega OT, where this is 0. Now, what will be the plot of current? Huh? Minus? Minus cos. Do you get minus cos omega OT if you solve this circuit? See, this circuit has a solution. Say, at t equal to 0, I is equal to 0. That should be satisfied because switch is closed only at t equal to 0. So, there is no current before closing the switch. So, if you take cos omega OT or minus cos omega OT as this expression for I, there is a problem. So, yeah, it is 1 minus cos omega OT. So, if I is 1 minus cos omega OT, what is average value? Average value of I is 1. Now, this goes against what, I mean, does it go against what we have learnt already? See, AC circuit, the current should just lag the voltage by 90 degrees. But it is not just lagging, it is lagging and getting shifted vertically. upwards. Now that is because this is a, I mean there is no resistance. So the DC value is not decaying. See, if there is a very small resistance, steady state would have been the one the waveform which we expect. Now this is actually an ideal circuit. We have ignored the resistance. It is not that resistance is 0, we have ignored it. So in any circuit that we study in engineering, when we say resistance is not there, it means that it is not there, it is ignored, it is a small value, that is all. So when we plot the waveform, we still say that it I mean I is minus cos omega ot in steady state. So what I want is in steady state. Okay. So it is because if I just look at this circuit, the solution is 1 minus cos omega ot. But if the circuit represents some physical circuit in practice, then it is an approximation. See, we are not worried. Say, to start with, we may study some circuits which are by itself. But as we go on, we are only considering circuits which represent some physical system. So when we are considering a circuit which represents some physical system, resistance equal to 0 does not mean there is no resistance. It just means resistance is negligible. That is all. Okay. So the steady state waveform will be equal to minus cos omega ot because resistance is ignored. That is all. I hope it is clear. Please note that there is a difference between studying this circuit as a circuit by itself and studying this circuit as a representation of some physical arrangement. That is all. So what we are considering is a physical arrangement. Please note, we are not considering some imaginary circuit. It's a what we are studying is the representation of some actual circuits which are there in practice. So by that argument, VB is a waveform which has a 0 average value. Okay. Now the question is, okay, can we get VA, VC? What is VA? Can I get VA, VC wave, I mean in terms of VB? So VA can be said to be identical to VB except that there is a phase shift of 120 degrees. So can I say that VA is VB of, okay, to be very precise, what I should do is I should write VA of omega ot is equal to VB of omega ot plus or minus, plus. Similarly, VC of omega ot is VB. Now, why I write in terms of VB is I have shown VB, we have got VB, that is all, is omega ot minus 120 degrees. So just take VB and shift it by 120 to the right, you get VC, to the left you shift it, you get VA, that is all. Okay. So, okay, now let us come back to this. Now the question is, what is the purpose of capacitor? So can you guess why I have put a capacitor? And there is a purpose which is actually hinted by the name itself, capacitor commutated converter. Sorry? To remove any? DC from where? Voltage source is perfectly sinusoidal. Now, if you are familiar with this term commutation, what is commutation? Okay, a current gets transferred from one valve to another. Now, to get that current transfer, one valve should turn off actually. So, the turning off is also, I mean, you would have studied commutation to be the word used even for turning off of a valve. Only when it turns off, the current that was flowing in that valve would shift to the another valve. So, capacitor is seen to help that commutation process. Now, when is commutation a problem? So, inverter operation is actually the operation for which the commutation margin angle will be small. So, we will see that for inverter operation, this having a capacitor on the AC side will help. Okay. So, let us see how it helps. So, alpha is the instant at which valve 3 is turned on. Now, if I take the duration alpha to alpha plus 60 degrees. Okay. Now, for this duration, valve 1 would have just been turned off. Okay. So, what is the voltage across valve 1? It should be negative for a long duration, that is what we want. So, what is the voltage across valve 1 in this interval alpha to alpha plus 60? So, we can try to get the expression for voltage across valve 1 from the circuit. So, alpha to alpha plus 60 means valve 3 is conducting. So, it is irrelevant whether valve 2 conducts or not, valve 3 is conducting. So, if by Kirchhoff's voltage law, valve 1 is not conducting, it has stopped conducting. So, the voltage across valve 1 is EA minus VA minus EB plus VB. Okay. So, let us plot, let us try to get the expression for VA and VB. So, it is EA minus EB. What is VA? What is the expression for VA? See, we already have the waveform of VB. Okay. Okay. So, let me try to get the expression for VB. For alpha to alpha plus 120 degrees. What is VB? Okay. So, what I will do is I will try to denote this minimum value as minus Vm, m for maximum value is plus Vm, Vm is positive. Of course, we can get an expression for Vm itself in terms of ID, C and omega O. What is the relationship between Vm, ID, C, omega O? See, we know that IB is C dVB by dt. Okay. Now, if I take omega OT between alpha and alpha plus 60 or 120, so up to 120 alpha plus 120, what is IB? IB is ID. So, this equation can be written as ID C dVB by dt. So, VB goes from minus Vm to plus Vm. So, the change in VB is 2 Vm divided by the time taken. So, it is linear, in fact, it is linearly increasing. So, the slope is constant for this 120 degrees. So, what is the duration? What is the duration? See, what I am trying to do is I am just writing the right hand side C dVB by dt. So, dVB by dt, the rate of change of VB with respect to time. It is 120 degrees. So, I mean, so 2 pi by 3 in radian by omega O. Is that okay? So, the time is angle divided by the angular frequency. So, this actually simplifies to ID is equal to omega O C Vm into 3 divided by pi. Okay. So, I can relate ID, omega O, C and Vm. Okay. Yeah, based on that. So, can I write the expression for VB for alpha to alpha plus 120? In terms of Vm, it is easy to write in terms of Vm. So, that is why I introduced notation Vm. So, what is VB in terms of Vm? See, it is just a straight line segment. See, from alpha to alpha plus 120, VB is a straight line segment. What is the equation of the straight line segment? That is all I am asking. Yeah? V Vm into sorry see, I want it as a function of omega ot, that's all. See, as a function of omega ot. We need not, I mean, it's easy to write it in terms of Vm instead of writing it in terms of Id. So let us write it in terms of Vm. Minus Vm plus Vm by pi by 3 omega t minus alpha, that's all. That's the equation of the straight line. So we know the expression for Vb. So okay, let me come back to the previous page. So why I want this expression for Vb is I want the voltage across valve 1, voltage across the outgoing valve from alpha to alpha plus 60. So that is in terms of Va and Vb. So we got the expression for Vb. What is the expression for Va? What is the expression for Va? We know that Va and Vb are identical except that Va leads Vb by 120 degrees. Okay, it may be easier if I, instead of taking it up to 120 alpha plus 120, if I make it alpha plus 60, it may be easier to write the expression for Va. What is Va? Huh? Why should it say? That's what I am saying. From alpha to alpha plus 60, what is Va? So what it is? It is nothing but Vm. See, from alpha to alpha plus 60, Va is Vm. See, you have Vb, shift it to the left by how much? 120. To get Va, you have to shift it, shift Vb to the left by 120 degrees. So for alpha to alpha plus 60, Va is equal to Vm. So we have the expressions for Va and Vb for alpha to alpha, from alpha to alpha plus 60. So substitute this in the expression for voltage across valve 1. So I have minus Va is nothing but minus Vm, and minus, sorry, not minus Vb, plus Vb. So plus Vb is minus Vm plus 3 Vm by pi omega ot minus alpha. So this is the expression for voltage across valve 1. Now, what is the voltage across valve 1 without a capacitor? It is Ea minus Eb. So with the addition of a capacitor, there are a few more terms. Now, because of these few more terms, will the voltage across valve 1 be negative for a longer duration? Okay, let me summarize here. See, what I am trying to say is, without capacitor, okay, so we are only talking about alpha to alpha plus 60 degrees. So for one interval for which what is the, I mean, we want to see what happens to the voltage across valve 1. So without capacitor, voltage across valve 1 is EA minus EB with capacitor. That means for the capacitor commutated converter. See, without capacitor means it is LCC, line commutated converter. This is LCC. So, capacitor commutated converter, CCC is in fact an abbreviation for capacitor commutated converter. So, with capacitor, voltage across valve 1 is in addition to this EA minus EB, I have minus 2 Vm plus 3 by pi Vm, 3 by pi Vm into omega OT minus alpha. Now, what we want for the voltage across valve 1, it should be as negative as possible for a long, for as long a duration as possible. Now, first of all, do you see that this voltage across valve 1 with capacitor is more negative? Minus 2 Vm plus 3 by pi Vm omega OT minus alpha. Do you see that it is negative? So, it is always negative. For alpha to alpha plus 60, it is negative. So, due to that, it takes longer for the voltage across valve 1 to become positive. So, it helps in commutation. That's all. That's the idea. So, the purpose of capacitor is only that. Okay. So, for inverter operation, we can go for alpha closer to 180. So, in the previous case of LCC, there was a limit on alpha. So, okay, one cannot go to values up to close to 180. So, now we can go even with even for inverter operation. So, voltage across outgoing valve. So, though I have taken just the example for valve 1, any outgoing valve is negative for a longer duration. Okay. So, this is compared with the situation of LCC, compared with that for LCC. So, this means that it permits operation with alpha close to 180. Close to 180. We have the expressions for VB, and of course, from that I can get the expressions for VA and VC. Can I get the expression for DC side voltage VD, and from that get the expression for the average VD? See, what is the instantaneous VD? First of all, one has to note that what will be the time period of minimum possible time period of VD? 60 degrees, 60 degrees. So, if I can get for any interval, say alpha to alpha plus 60, what is VD? So, for alpha to alpha plus 60, what is VD? Then from that get the average value of VD. Okay. So, I would suggest that you please try to get these things. Okay. Now, there are a few other things which are very easy. I would also suggest that try to get the expression for RMS value of voltage across capacitor. To be precise, RMS value of fundamental component of voltage across capacitor. Okay. So, please try to get these expressions. I think they are straightforward. I will not be trying to I will not be trying to do this in the class, but I will give the answers. Okay. So, we will stop here, we will continue the discussion on this in the next class.